Okay, let's continue our discussion. So in this video, we are going to discuss about stress and strain. What happens when an external force is applied to a body? This external force can cause deformation in the body. And let's take this body is at rest to make the situation simple. This deformation mainly depends on two things. Number one, the strength of this applied force and the nature of the material or nature of the object on which this force is being applied. So, strength of this external force and nature of the object. Okay. And while this deformation taking place, there is a counter force which tries to counter this externally applied force. And this counter force, let's say this is only F for timing. This counter force we call restoring force. And we have discussed such an example in case of a spring. If there is an external force being applied on this spring, this spring also exerts a force to counter this external force. Let's say this is a spring force. So in this particular scenario, this is deforming force and this force is restoring force. Okay. Now this restoring force per unit area is called stress. We can write restoring force per unit area, and this quantity is called stress. And we know that restoring force is also a kind of force, so its unit should be Newton in SI system, and this area has unit meter square, and you can easily figure out this is unit of pressure, which we used to call Pascal also. Now what about dimensional formula for stress? You can write dimensional formula for stress as dimensional formula for the force is ml t to the power minus 2 and divided by this L square. This is length into length. So you can write it ml to the power minus 1 t to the power minus 2. So we have discussed about stress in general. Now let's take its three different types here. So we will start from one dimensional situation. Here we are going to discuss tensile stress or compressive. This is M. Okay. Compressive stress. Okay. Let's take an example here. If there is a cylinder, let's say a thin cylinder, and an external force is applied on its circular face here and here also. Same magnitude but in opposite direction. So this will try to elongate this cylinder, and in this case there will be a restoring force acting against this external force. Let's say this is a perpendicular. Why I am writing? Because these forces are being considered to be perpendicular to the surface here, this circular face, perpendicular to the circular face. And there will be another force which is countering. These two forces are equal and opposite in direction. Now, this restoring force F perpendicular per unit surface area, this surface area, circular surface area, let's say this area is A. We call it tensile stress. And what about a force which is here? I am writing that a force which is trying to compress this narrow cylinder or thin cylinder. Let's say there is a pair of forces and one is acting here, F external, and another is acting on this lower face here. And let's say this is also F external, equal in magnitude, opposite in direction. Now, in this case also, there will be counter force here, and there will be counter force. This counter force is restoring force, and again this restoring force we can write per unit area. So in this case, in second case, I'm writing here restoring force per unit area is compressive stress here. Now, if these forces are being applied, there will be change in length. So let's take one such case here. If the length of this cylinder is L, and after application of this force, let's say there is change in length, which is delta L. So we have one more quantity here to define, and that quantity is longitudinal strain. If we are taking change in length per unit original length, this quantity is longitudinal strain here, and its SI unit and its dimension. I am leaving that part to you. You have to figure out what is its SI unit and what is its dimensional formula in case of longitudinal strain here. Okay, you may think that due to this force, if the length of this cylinder is changed, then there will be change in diameter if its volume is constant. So yes, this is the case. Its diameter will also change. But for now, let's take this cylinder is very thin so that we can just neglect the change in diameter, which is not a big quantity compared to this change in length. So with this argument, we can focus on the longitudinal strain. Later on, we will also introduce that part here. But for now, let's take longitudinal strain. Okay, now moving to the second kind. Here we can call it tangential stress, or let me write it first. Tangential stress or shearing stress. Okay, let's take an example of the cylinder again. Here we have a right circular cylinder, and okay, here we have right circular cylinder, and there is an external force, being applied on this face here, and another force is being applied on this face here. Okay, so to counter this force, let's check this one. There will be a restoring force, and this restoring force will be parallel or tangential, you can say here, with this surface. So in this case, we call this force per unit area. Let's take this area to be A. We call it shearing stress or tangential stress. This is this ratio, shearing stress or tangential stress. Okay, another force should be here countering this lower one, F parallel. Now, there should be some change in its configuration, or there should be some change in its dimension. And for that, we are going to define a strain also. So let's take after the application of this force F external here, there is change in dimension of this cylinder, and this cylinder comes to a new shape here. Okay, again, this cylinder comes to a new shape here, like this. This is its circular face. This is its lower circular face. Okay, and initially it was here up straight, and now it has tilted. In this case, let's take this angle is theta, and this distance from here to here is x, and we know this is length. Okay, I have drawn this thing very big, but this length is very small if we are talking about some solid bodies like steel or like iron. This is a kind of a small thing. So this theta is usually a small, but to be visible, I have drawn it on a large perspective. In this case, there will be shearing strain also. So the shearing strain, we can say shearing or shearing strain. This shearing strain is this change in position here, delta x by L. And yes, this is shearing strain. Okay, delta x by L, you can write it as tan theta also in this right angle triangle. This is tan theta. And for very small theta, this can be nearly written as theta, a small angle approximation. We have done this thing several times. So you can write shearing strain delta x by L, or you can write it theta, the angle by which this body has been tilted. Now moving to the third one, hydraulic stress. Hydraulic stress. Let's take a situation where this cylinder has been kept in a fluid. Let's take this is a container, and in this container there is fluid, and the pressure inside this container is P. And if this cylinder has been kept here inside this fluid, the pressure on this cylinder will be P. And to counter this external pressure, let me write it Pxt. To counter this external pressure, there will be pressure exerted by this body on the outer environment or on the fluid here. So the restoring pressure, we can say, and then this restoring pressure per unit area of this body, we call it hydraulic stress. Okay. Now there will be change in its volume also, because this is being applied from all around. This body has been dipped into a fluid where this fluid is applying pressure, let's say Pext on this body. So there will be change in its volume also. And for that reason, we are going to define volume strain. So let's take the change in volume is delta V. Then the volume strain will be change in volume, and if its initial or original volume was V, this will be change in volume per unit original volume. And in real life, this situation happens when a submarine goes inside water. Okay, so this is all for this video. In the next video, we will continue with Hooke's law and stress strain curve.